In the previous lesson, we have been looking at MapReduce, and actually we ran a real MapReduce job. And now what I'd like to do is take a look at what happens behind the scenes in a Hadoop cluster. And again, most Hadoop is run on a cluster. However, it can be on a single node. And we'll talk more about that a little bit later. So as an example, there's a chart that I've put together here to indicate the data flow through the MapReduce process. And I think for many people, this helps clear up some possible misunderstandings or fill some gaps that they may have missed in other explanations. To begin, there's the input step all the way on the left. And in this case, we don't have War and Peace. We've got a little snippet of text called see spot run spot run, see the cat. And this is the words that we're going to count. And to keep the example simple, obviously it's a small number of words. So the first thing that happens in the reduce process is the split. And that is, we're going to split the actual input up into our blocks of data that are going to be searched in the map process or run through the map process. Now the blocks of data usually are chosen to match the block size in HDFS so that they map real well into the file system. And these are going to be big blocks in the case of HDFS. In this case, obviously it's a small 3 words in a line, so we're not really talking about huge blocks at this point. In any case, we split the file up into 3 separate blocks, and each block is going to go to a different mapper. And the mapper is going to count the number of words in the block that it gets. So again, this is where we start to see the parallel piece come out in the mapping process. And so we can see in the first case in the map column, the see spot run, each words are there 1 time. And the second block, we see that run spot run, well, the word run is there twice, but we don't put that down as 2, we only count it as 1 because that's the way our mapper works. And then the final one, see the cat, obviously, you get the idea what we're doing now. Now we move over to the phase called the shuffle phase. And this is necessary because before we do the reduce, what we've got to do is take the output of the mappers and sort them according to their primary key value, which is going to be the word. So the map produced key value, a key value pair, in this case the word and the count. And then what we need to do is collect those in the shuffle process. And this all happens transparently to the end user. All the key value pairs, for instance, for C, are moved up to the one top shuffle process, and they're collected there. And then the spot, run, the, and cat, similar words, are all get shuffled to collect all those together. So this process is one of the points where there is data movement within a Hadoop process. Depending where the reducers are running, these shuffles may move data across the cluster. At this point, once the data have been shuffled, they can move into the reduce step, and basically the reduce step is going to sum all the similar key valued instances. So in the case, we're going to count the words in the reduce, so we see C for 2, spot for 2, run for 3, the 1, and cat 1. So it's obviously a trivial example. And then finally, we combine the output. And this is pretty much a standard way in which the data flow happens with MapReduce. An important thing to remember, the data flow is one direction. And we'll talk about this a little bit later, about how this can affect some of the properties of the system. Now I'd like to talk a little bit more about how the actual cluster nodes factor into this process. So what we have here is a diagram depicting what I just showed you without all the data, and it has the mapping and shuffle and reduce step. So in this case, we're looking at basically a 3-node cluster. And how this all works out is there is a main process in Hadoop called the job tracker. And this is running on what's known as the job tracker node. And again, this can be virtually any node in your cluster, but there's usually a main node where you run many of the important daemons, such as the name node and the job tracker node. So the job tracker is really the guy that keeps track of everything that's going on. On all the individual nodes, there is something called a task tracker. And the task tracker manages what's happening on the nodes. So what will happen is, when a job initially gets run on Hadoop, the mapping process, the job tracker will look for nodes that have the data that we need, that the data has been replicated and lives on that node, and will attempt to contact that node's task tracker and say, I need some mapping done. And can you do this number of processes? Now, the number of processes is set up in a configuration file and can be adjusted depending upon the node type and cluster, etc. If the task tracker is got some free time, it's going to say, sure, give me some work to do. If it doesn't, the job tracker is going to look for another task tracker that has a copy of the data on its node as well. Now, if it doesn't find any nodes available that don't have the data directly on their hard drives, it's going to assign it to another node, but there may have to be some transfer of data from node to node. So that's the worst case. Ideally, what we're trying to do is move the computation to the data. Once that happens, the mapping processes start, and that's why in our previous example, when we looked at the actual running MapReduce program, all the mapping happens first. So the data gets mapped, and now we come to the shuffle phase where, based on the key values, the data are shuffled around. Now, one thing to notice is node 1 also acts both as a mapper and a reducer. And same with all the other nodes. They generally operate as both mapper and reducer nodes, and largely because as the mapping gets done, nodes become free and they can be used for the reducing process. So there's a shuffling process, again, figured out behind the scenes, that figures out what keys are going to be sorted on what node. And of course, in node 1, the most advantageous situation is where keys produced by the mapping process on node 1 are used by the reducing process on node 1. That would be a huge benefit in terms of less data transfer. Generally, that's not always the case, and you have transfers needed to other nodes. So in the picture depicted here, we see there's a shuffle exchange step where the like key values are sent to different nodes. And the number of reducers that run on a node depends upon, again, some configuration values, but it can be more than one reducer per node. There can actually be many reducers on a node, as there can be many map processes on a node running at the same time. Once the reducers get their data, they again start working on reducing the data, whatever the reduce step is that they've been told to do. Also, similar to the map process, when the job tracker is looking to place reduce tasks, it will contact the task tracker on individual nodes and see if they're available to run the mapping processes. So the actual shuffle piece depends upon really where jobs are placed and is very dynamic and happens at runtime depending upon the load that's hitting the cluster. So once everybody gets, all the mapping is done and all the key value pairs get pulled down into the reducing process finishes and creates the output. In this next slide, I want to go back to a little thing that was mentioned previously called a combiner. And if you were noticed in our simple MapReduce process that you looked in the map stage and said, well, gee, you know, it's mapping and it found the word run and it found the word spot and then it found another run. Why doesn't it just say, hey, I found 2 runs, instead of sending over the shuffle to the reducer the 2 instances of run, comma 1, basically? Well, that's exactly what a combiner does. And what it says is, hey, look, I'm going to lighten the load here and I'm going to optimize this a little bit, and notice that I've got 2 instances of run and I'm going to report them as run 2. So when it gets to the reducer, it actually makes for less work. So a combiner step is recognizing that there's a little bit of an optimization that can be done with the output of the map data before it goes off to the reduce stage. And the combiner can be used for any type of processing that makes sense. And of course, you're only going to be doing optimizations within this subset of key pairs that you have, and it's going to have to go to the reducer to get done globally, to get combined globally. Another thing to mention is that it is not necessary that a map reduce process actually have a reduce process. And it certainly could happen that you could run things through a mapper and be finished, or run things through a mapper combiner and be finished, and not necessarily have to use a reduce step. It really all depends on your application. I'd like to talk about fault tolerance and speculative execution in Hadoop. These are interesting and important properties of Hadoop, largely because we're going to be running jobs on large, big clusters of commodity hardware. And as anyone knows, large numbers of anything have a tendency to break. And fault tolerance is important because we want to be able to have Hadoop run while things may break or there may be issues with hardware. And then I'll talk about an interesting thing called speculative execution that Hadoop does as well. The first thing to understand that because of the MapReduce process and the way it's structured as a functional process, faults can be handled by restarting tasks. And as you recall, there is a switch master called a job tracker that is basically a task master, in a sense, that's going to decide what happens where and what work gets done where. On the nodes, we have our task trackers. And should a task tracker stop communicating with the job tracker, well, then the job tracker is going to assume that something's happened to that node. And usually it's referred to as a heartbeat. And if it doesn't get the heartbeat in a certain amount of time period, it's going to assume the node is down. So whatever processes, whatever maps or reducers are running on the node, the job tracker knows that and is going to basically restart those jobs on other functioning nodes. The important thing to remember is that the nodes that are running will be able to redo work that maybe was already done on another node, and then will continue on and pass their data on to the next node. In the case of the reducers, it's fairly simple because if they've failed, you can just restart and go back and get the data from the mapper and restart the job. If the mapper breaks, well, then we've got to really start the process, that map process again, and move things forward. So there is this redundancy built in where there may be jobs that need to get redone because a system went down, stopped working, and didn't report in. One important thing to realize, however, is the job tracker can handle task trackers going down. So nodes can go down, and it can pretty much manage things. And obviously, the more nodes you have, the more duplication you have, the more redundancy you have. If the job tracker goes down, that node that's running the job tracker, then the show's over. There's no way to recover from that, and every Hadoop process stops. So that's the central command that needs to stay up during the Hadoop process. The ability to deliver all this kind of nice fault tolerance is really due to the fact that none of these processes create any side effects in the whole process. And if you recall from the diagrams that I had shown, none of the mappers communicate with any of the other mappers. None of the reducers communicate with any of the other reducers. The only communication that happens really is when we do the shuffle phase, and that's a very constrained, specific communication step that produces no side effects and can be easily reproduced. So side effects are things that program state is often referred to, of things that are unique and start to create, say, a unique mapper process that needs to somehow be reproduced using specific state from maybe a different mapper process of some sort. So we eliminate all those in Hadoop. And because there are no side effects, and as you recall from the one diagram, their data flow is in one direction. And the data paths, other than the shuffle step, are perfectly predictable in a sense that we know which data, where data came from, where it's going. We don't change any original data. We can redo everything we wanted to do. So that's a big bonus for Hadoop, is the fault tolerance. On the other side of fault tolerance is an interesting concept called speculative execution. And what that basically says is, if I have excess capacity or I have nodes not doing anything, what I can do is start jobs in a redundant fashion. For instance, I have a lot of extra nodes and I have a lot of map processes running. I can actually double up the number of map processes and rerun them while they're still running on other nodes. Now, why would I want to do this? Well, perhaps one of the nodes that's running the map process decides to break or has a bad hard drive controller or some other issue that's slowing it down. So basically, the first node that gets done with the reduce process contacts the job tracker and says, I'm done. Well, then the job tracker sends a signal to the other task tracker that's doing the same job and says, hey, buddy, you're done. And you can stop working. Someone else finished before you. So this is kind of like a forward insurance to make sure that if some event does happen, some fault does happen, we've already got redundancy happening in our system. And this is why running Hadoop can be a very safe process, in that even though there might be systems work that needs to be redone due to a system going down, that work might already be being done at the same time on another system, just in case, if we had the extra capacity. So it's an important aspect to the MapReduce process. The important thing about the speculative execution is that it helps prevent bottlenecks that may develop around problems with a node. Possibly there's congestion or a fault in an Ethernet switch of some sort, getting data on and off of a rack where you may have had a job running on a different rack and may be able to communicate better. So it basically is the best of both worlds. And again, the reason we can do that is because we have a predictable communication path and side effect free processes in our complete parallel process.